Hi, this is Shirley Physics doing an episode on math supporting physics. I call it calculus express derivatives. Here we're going to be talking about change. Calculus is a kind of the math of change, and a derivative in itself is mainly thinking about the change in a function, looking at the change. You might also consider that the slope shows the change at any point along that function. So I do have on this MSP, stands for Math Supporting Physics worksheet, a little introduction there for you to read. So after you read that and look at these two functions given, that they are related, even though visually they don't look very much the same. But if you do start tracking, like from the beginning of this first function towards the end, it starts out with a high rate of positive change, and then at this point at the very top of the slope, it becomes a zero change. As you move down, becomes a negative change, so that change is going to increase, and then that change is going to decrease in the negative direction, become a zero slope again. So there's a zero change there. Now if we start thinking about those patterns and look over to the right, these values start out in the higher range of positive values, and it approaches zero. Then it becomes a negative value and turns back around again and hits zero. So if we look at this slot here and this slot here, these 2 points, they correspond to the two zero slopes. Everything before this shows a positive but increasing change. Here are positive values. Did I say? Here it shows a positive but a decreasing change. It slopes less and less. The slope becomes less positive there. So I made a little bump there. So our values start out positive, become less and less and less, and approach zero till we get to this point. And now we have this second segment. I'll call it red. Now the first part becomes a negative slope and increases that negative slope. So we've got an increasing negative value here. And at this point, that negative slope starts to lessen to become zero again. So we've got a lessening negative values down below the line. And the next segment, we'll go green, becomes more and more positive, and then less positive. Here we have more positive values and then less positive. So comparing the slopes on the graph on the left to the values on the graph on the right, we start to see that there is a connection here. And finally, that last segment, just to kind of bold it here a little bit, the values are negative and becoming more and more negative. And sure enough, over here, we've got negative slopes becoming more and more negative. Now, I don't think this will actually plateau or anything. This should just kind of go down as an asymptote. But that is what a derivative is. It's a function that describes the change of another function. And notationally, if we have a function f of x, like we see over here, you'll notice that there's a notation f prime x is the derivative function of f of x. Okay, so that's just a communication in math talking about a derivative. Now there's another notation I'm going to teach you on the back of this. So the first thing I'd like you to do is sketch each of these functions and then try to visually come up with their derivative function. So if f of x equals x is plotted, we should get a line. Let's see, I've got a line tool over here that should work. Okay, it should just be a line that looks a little something like that. So what would the derivative function look like? So if you think about the slope, does the slope of this line ever change? It doesn't. So it's a constant positive slope that doesn't change. So the function over here for the derivative should not be zero, because these are not zero slopes, but it should be a constant positive value to match the constant positive slope. So if I take a line that's just about horizontal, that shows a constant value that's positive, that's greater than that 0 value. So there's the derivative. That would be a sketch of the derivative function of f of x. Over here, if I sketched a quadratic, I don't have a good tool for that, so I'll just draw it out here. So we might have a parabola, that type of thing on both sides. Here's my sketch. All right. So now over here, what would the derivative look like? Well, these slope values are very negative. Okay, they're very steep. And then as we get closer to 0, that slope evens out till we get to 0. So we should have some very low numbers, low values for the slope, and it approaches 0. And then after that, that 0 slope increases again, the slopes increase. So these values will increase. And turns out this derivative of a quadratic is going to be something like a straight sloped diagonal line. How about the cube function? So if we do that, it's more pronounced than the quadratic, but it does have some negative values. So that cube function will look like that. All right, so what about the derivative of that function? So here we should have some, oh, look at this. All of these slope values along here are positive. That's interesting. So we have some positive slopes, and the slope decreases to 0 and then increases positively again. So all the values of the derivative function are going to be positive. Now they start out by decreasing and then hitting 0. We do have a 0 slope right there at the point 0, 0. So there should be an intersection at 0 here, but the slopes are positive. So the values here are going to be positive, and they're going to curve to 0 and then curve back up to become positive again. So guess what? From a cubic equation, we're going to get a quadratic out of it as the derivative. All right, so do you see a pattern here? The derivative of a slope line, of a constant line, is a constant. Derivative of a line is a constant value. The derivative of a quadratic is a slope line. The derivative of a cubic is a quadratic. Do you see how we're like taking that x, and this function down here is something like an x to the, if this is x to the n value, this one down here is an n minus 1. All right, so in this case, this would be like x to the first power, and a constant would be like an x to the 0 power, which is 1. Now if we do put a constant in front like a, in this case a might be 1, all right, then we would also put that same constant in the front over here. So if this was a 2x to the first power, then down here we would have 2x to the 0 power. So this might be up here at like, that's 1 and then 2 along the y-axis there. So what we see here is something called the power rule for derivatives. And that's what's defined out in front. Now there's one extra aspect here that I couldn't really bring about from the sketch, is that that n, when we take a x to the n and take the derivative to find its slope function, then that n value does come into the front. And I should correct this completely. The whole form, because remember I put that a in the front. If we have a x to the n, then the complete definition here would be a n to the x, or times x to the n minus 1 power. All right, and that's what we're practicing down here. I believe it'll bring it out as we go along there. So remember that a, that any coefficients in front of the original equation will remain, but we will be multiplying also by that n value. So try it out on the next 3. Pause this video now if you want. I'm not going to pause my speech though. And I'm going to fill out a few of these just to get you started. So if you're done pausing this video and you've started it back up, what is f prime x? Well, here we have x to the 1 power. So that means our derivative is going to be, there's no coefficient in the front. So we're going to bring that 1 down. The n is 1. So the answer is going to be 1x to the 1 minus 1, which is x to the 0 power, which is 1. Right? Any number to the 0 power is 1. Okay, and then our next one, f prime of x. We're going to bring the 2 down. N is 2 in this case. So 2x to the 2 minus 1. So I'm taking that x to the n turns into an nx to the n minus 1. So that's a 2x to the first power. 2 minus 1 is 1. So that result is 2x. And if you did the third one, f prime x, it's going to be 3x to the 3 minus 1. So that's 3x squared. And that's how you work it. You're doing calculus. This is the power rule for calculus. So if you take this function, then this function will be the slope value function of it. Show the change. I gave some examples here. You can work them through or just look at them. Just to skip the first one here, look at the second one. What happens to the derivative of a constant? Well, is there any change in a constant? No, there's no change. So what's the derivative of 5? It's 0. There's no change to 5. So there's actually a little hidden 0 out front here. That 5 becomes a 0 as a derivative. Is there any change to 10t? Well, yes. It changes by the slope. The slope is 10. So here we have a 10t to the first power, and that becomes 10 times 1 t to the 0 power. Now 1 times 1 is 1, so there's your 10 by itself. Now here we start to see the coefficients out front. So 1/2 of 10 is 5. Okay, so I'm just going to take this little piece here and talk about it over here. If we're starting out with 1/2 times 10t squared, that's negative 5t squared. Now if we take the derivative of that, we're going to keep the coefficient out front of negative 5, multiply by n, t to the n minus 1. See, it's just a practice thing. Once you get used to it and practice it a bunch, then it just starts to become old hat. So after this, negative 5 times 2 is negative 10 t to the first power. So we get that negative 10t term out of that, minus 10t. Okay? And you could combine like terms if you wanted to. You don't have to do that in this exercise. We're just practicing the derivatives. So here, down here, you're going to get some practice out of it. Now, some funny symbols are going to start showing up. And the question is, what do you do with these half powers? So if you've got a square root or a half power, remember, it's probably easier to look at this one, for example, as 2x to the half power. All right, you want to change that before you try to take a derivative, or else it'll be a little funky. And this piece right here, so 1 over x squared becomes x to the negative 2. Just change it to that before you go and take the derivative. So once you have this n value, n would be negative 2 in this case, n would be 1/2 in this case. Up here in the example, we've got t to the 3/2. So first we're going to take the derivative of 5 is 0, so there's 0 change with a constant. And then we've got this negative t to the 3/2 power, so n is 3/2. So out of that, we're going to take a negative 1 is the coefficient in front, so leave the negative. Then bring down the n, so we're going to have a negative 3/2 t, so this would be n t to the n minus 1. The n is 3.5, or 3/2, and if you subtract 1 from that, you're subtracting 2/2. So 3/2 minus 2/2 is 1/2, and that's where we're getting that final answer there. Okay. So if you do start out with a let's say in this, do we have one down here? I don't have one. If you did, oh yeah, here it is. If you have x to the 1/2, if you subtract 2 halves from that, which is 1, you'll end up with an x to the negative 1/2 as that exponent power there. So I'm going to give you the rest of these to try out. You can pause this video and do 1 through 8. You can check the answers if they are left for you. And after you're done pausing this video, if you want to check out this new notation down here, I want to talk about it. This is the notation we're going to be using in physics class. It's more specific because oftentimes in an equation you might have more than one variable or unknown or something like that. So if there's more than one variable that might be changing, we need to be able to specify which one we're taking the derivative of. So which term is showing the change. For example, in this first one, a might be a constant. So your answer will be in terms of a. But a is not what's changing here. X is what's changing with respect to f, the function f. So we might say take the derivative of f with respect to x. And so in the example here, if we're taking the derivative of f with respect to x, then a is just going to be part of the coefficient. It's not going to change. So if a is the coefficient, then derivative of ax squared is going to become 2a to the n, 2ax to the n minus 1. So that's where you're going to get 2ax to the first power out of that. And the derivative of x to the first power is x to the 0 power, which is 1. So that's why the b is still left over there. So whenever you see this notation, it's saying take the derivative with respect to x for this example, but leave everything else as a coefficient in your brain. Okay, so that is that notation. You're still doing everything the same way. So try those out and check your answers. I hope this is helpful in getting you started. This is all you need to know for the beginning of our physics class. How does a function's derivative look? And that's the slope. The function's derivative is the plot of the slope values. And here we're working on actually coming up with the derivative using the power rule of some functions. Okay, hope this is helpful.